So, we said last time that the alpha protons are acidic, and you need to get an idea of what we mean by acidic. How acidic are these alpha protons? In order for you to do that, you should take a look at the pKa of these molecules, and I want to also introduce you to some other alpha carbon hydrogens as well, not just ketones. If you take a look at some of these compounds, you see that for example, aldehyde and ketones, the pKa of these alpha protons are around 20. All right. One thing to note about aldehyde is that this proton, right, that is attached directly to carbonyl, is not acidic. And a lot of times students make that mistake and deprotonate this, but notice if you deprotonate this, you cannot have these resonance stabilized enolates. So that's why this is not something that you will pull off. But these alpha protons are acidic, and the pK is around 20. Now this compound in the middle with the two carbonyls, so the alpha carbon hydrogen here is going to be around 20, just like here. But notice this alpha proton is even more special in that this alpha proton is between two carbonyls. All right, so this is a special case in which you could imagine you could draw a resonance structure with this carbonyl as well as this carbonyl, so it's like doubly resonance stabilized. So pK of this proton right here is around 9, which is a lot more acidic than the usual alpha carbon hydrogens next to carbonyl. So this one right here will be about 20, but this one right here will be about 9. All right. So we're not restricted to the alpha carbon hydrogens next to carbonyl, but any electron withdrawing group will serve the same purpose. So this is a nitrile, but you could have same thing happening if there's a nitro group. So the alpha would be over here. These hydrogens would be more acidic than these other ones, and this pKa is around 25. And then here, I just want you to note that we have these alpha hydrogens around 20, but you also have to note that these, even though it's really far away, are also acidic around pK of 22. And the reason for that is because you have a double bond really connecting. So if you put a negative charge here, you could draw a resonance structure all the way through the C double bond O, right? Whereas if the double bond wasn't there, then these protons would not be acidic. All right. So we keep saying that these alpha hydrogens are acidic, but you have to kind of pull back and look at in terms of, you know, how acidic are these compared to other organic compounds. All right. So that's why I have these compounds below. So alkanes in general, if you want to pull these protons off, is really hard because the pKa is around 50. Contrast to that, if you have electronegative atoms, so an alcohol or water, those hydrogens are the pKa is around 16. All right. Whereas carboxylic acid proton, we went over this in the acid family in Unit 3. You know that the pK of this is 5, right? So even though we keep saying these alpha hydrogens are acidic, compared to carboxylic acid proton, they're still not as acidic. Okay, so look at the numbers. The lower the pK, the more acidic. So that's why out of all the organic compounds, we say the carboxylic acid is the organic acid. And notice, you know, the pK of water or ethanol, some of the alcohols are around 16. So the hydrogen on the oxygen is more acidic than the hydrogen on the carbon, even though it's resonance stabilized. So you have to keep that in mind when you're looking at these compounds. But notice though, this hydrogen on the alpha carbon, because it's flanked by 2 carbonyls, is a lot more acidic than hydrogen on the oxygen. So it's very situation dependent, and you have to ask yourself, you know, the hydrogens that is attached to what atom, and then is, you know, and then you have to ask yourself, you know, how well is the resonance stabilization working in this. All right. So the reason why I bring up the pKa's of these compounds, especially compare and contrast the pKa's of the alpha protons, is that remember in the last page we looked at, you know, how we're going to make these nucleophiles, and it depended on whether or not we used catalytic amount of the weak base or we use strong base to form the enol versus the enolate, right? And they're going to have different properties as a nucleophile, because one is neutral and one is negatively charged. And then when they go on to react with the electrophile, even though they give the same product, the yield will be different, and this is all dependent on the condition. All right, so we're gonna look at what are the conditions that form enols, and then we're gonna follow that up with what are the conditions that form enolates, and then subsequently we'll be looking at the reactions. All right, so let's define what tautomer is, because that's a word that we're going to be using a lot, and so I'm going to define it first, and then we'll look at examples, and then I'll go from there. So tautomer, definition of tautomer is interconvertible structural isomers that differ only in the location of double bond and a hydrogen. All right, so when we draw the enol, so if you actually look at any carbonyl compound in detail, for example acetone, it actually exists in 2 different forms, and the 2 different forms are called tautomers. So I'm gonna draw the arrows both ways. All right, so this would be called the keto tautomer, and the enol version of it, where the hydrogen is removed and goes to the oxygen, and then the double bond is between carbon and carbon, not between carbon and oxygen. This would be called the enol tautomer. Now, for something like acetone, these 2 species, distinct species, are rapidly interconverting, all right? But because the keto tautomer is so much more stable than the enol tautomer, this exists in like 99.9%, whereas this is less than 0.01%. All right. So the arrow really should be, major, big arrow going back, and then like a little teeny arrow going to the enol form. But these two compounds are distinct species. They coexist, and for most carbonyl compounds, this is the the population that you're going to have the more stable keto form in majority, and then very, very, very small quantity of the enol form. But you have to realize that the enol form does exist. All right. Now, many people get the tautomers mixed up with the resonance forms, and in resonance, okay, so if we draw a resonance form, right, like for enolate, so this would be a resonance structures, right? Now, when we draw resonance structures, this is not a distinct species, and this is not a distinct species. In other words, they're not chemically distinct species. And remember, the resonance structure is just the movement of the pi electrons. None of the atoms has moved, all right? Whereas here, the hydrogen atom has moved from carbon to oxygen. So these are structural isomers that are distinct. Whereas here, only thing that we're showing, because we have problem being able to draw with one structure what that compound really looks like, the negatively charged is not just residing on the carbon, but also on the oxygen. So the more accurate form, if we could draw it in this way, is with the negative charge in between, like this. So this, there's only one distinct species, and we're trying to be able to draw where the negative charge resides. Some are on the carbon, some are on the oxygen. That's resonance. But that's totally different from tautomers, okay? So for example, for some tautomers, in this diketone example, actually the equilibrium exists more to the right than the left, and it looks like this. So this enol form exists in greater than 80%, and this keto form exists only in 20%. So when you have this compound in a solution, you have to be aware that majority of this doesn't exist in this form, but exists in this form, the enol form. And how do we know that? If we put this compound in a solvent and look at the NMR, you could tell exactly what the population is by looking at the integration of, for example, this proton of the alkene versus the ketone that will show up totally in a different way. And then when you look at the area difference, you could tell the population. All right. So I'm going to end here and continue on in the next lecture.